The unit circle. We began developing trigonometry with right triangles with a hypotenuse of 1. The side opposite a given angle equals sine theta, and the adjacent side equals cosine theta. Since there are an infinite number of possible angles theta, there are an infinite number of right triangles with a hypotenuse of 1. Here are a few. We also learned in geometry that the distance between 2 points is equal to the hypotenuse of a right triangle constructed with the sides along the horizontal and vertical axes. That means that if, for each triangle, we locate theta at the origin and have cosine theta lie on the x-axis, the distance to the end of each hypotenuse will be 1 for every triangle. What shape is formed by an infinite number of points that are an equal distance from the origin? Discuss. Here's what the triangles look like when laid atop one another with angle theta at the origin and the side labeled cosine theta on the positive x-axis. This is the result in quadrant 1. Let's keep going. How should we fill in quadrant 2? So if we take those same triangles and flip them to the other side of the y-axis, we fill in quadrant 2. What about quadrant 3? If you take these points and reflect them across the x-axis and then draw those lines in, we have filled in quadrant 3. What about quadrant 4? Finally, we can reflect these points across the x-axis, we can reflect these points across the y-axis. Either way, we have our quadrant 4 triangles right here. This is showing the 5 triangles reoriented with theta at the origin, cosine theta on the x-axis, and sine theta reaching up or down to the unit circle. Of course, there are an infinite number of possible triangles. Here are just 5 reflected around the unit circle. With the exception of the x and y intercepts, you can draw right triangles that fits the scheme in all 4 quadrants. In this presentation, the Greek letters alpha, beta, and theta will be used to identify angles with degree measure. In contrast, the letters T, U, and V will be used to identify arcs and angles in radians. In diagrams, angles will be labeled at the origin. Arcs will be labeled on the boundary of the unit circle. This convention is designed to help recognize and understand the subtle difference. The unit circle is the circle centered at the origin with a radius of 1 unit. Its equation is given by x squared plus y squared equals 1. For any point xy on the unit circle, the first coordinate x equals cosine theta, and the second coordinate y equals sine theta, where theta is the standard angle in degrees whose initial side is the positive x-axis and terminal side includes the point x, y. Here we have the definition of the unit circle, but with t, which is measured in radians. For any point xy on the unit circle, the first coordinate x equals cosine t, and the second coordinate y equals sine t, where t is the standard arc on the unit circle from 1, 0, terminating at x, y. So this arc right here. The tangent ratio, given by tan t, is the ratio of sine t to cosine t. So tan t equals sine t over cosine t. For any point xy on the unit circle, the slope of the radius from 0, 0 to x, y is given by m sub r equals tan t, where t is the measure of the arc on the unit circle from 1, 0 terminating at x, y. And remember, t is measured in radians. The equation of the unit circle is given by x squared plus y squared equals 1. By definition, x equals cosine theta and y equals sine theta, so substitution produces a new equation. In terms of theta, the equation of the unit circle is cosine squared theta plus sine squared theta equals 1. So here we have the unit circle. Quadrant 1, we have cosine theta and sine theta. In quadrant 2, we have a negative cosine theta value and a positive sine theta value. Here we have negative values for cosine theta and sine theta, and here we have positive cosine theta values but negative sine theta values. Given any point xy on the unit circle, a radius can be drawn creating the terminal side of an angle theta with the positive x-axis. Step 1. Pick any point xy on the unit circle. So we've picked this point here. Step 2. Now draw a radius from x, y to the origin. Label the angle between the radius and the positive x-axis with theta. So we draw this purple line here, and we label this angle theta. Step 3. From the point x, y, draw a vertical segment to the x-axis and label it sine theta. So that's this red line right here. Step 4. From the point x, 0 right here, draw a horizontal segment to the origin and label it cosine theta. So that's the green segment right here. The indicated radius makes an angle of 60 degrees with the positive x-axis and has a terminal point on the unit circle, right here. First, construct a right triangle and label legs with sine 60 and cosine 60. So if we drop the line right here, this is a right triangle. Cosine 60 is going to be this right there, and sine 60 will be this side right there. Then determine sine 60 degrees and cosine 60 degrees using a calculator if necessary, and use these values to label the terminal point. Cosine 60 degrees is 1/2, so that makes this piece right here 1/2. Sine 60 degrees is the square root of 3/2, so that's the length here. The decimal values of 1/2 and the square root of 3/2 are 0.5 and 0.87. So those are the coordinates of this point. The standard arc T measures 3π/4 radians and terminates at a point on the unit circle as shown. Find sine t and cosine t. First, construct a right triangle and label legs with sine of 3π/4 and cosine 3π/4. So we just drop the line down right there. This line right here is going to be sine 3π/4. And this length right here is going to be cosine 3π/4. Then determine sine of 3π/4 and cosine 3π/4 using a calculator if necessary, and use these values to label the terminal point. If you use a calculator, you'll see that the cosine of 3π/4 is negative 0.707, and the sine of 3π/4 is positive 0.707. So those are the coordinates of this point. You can also leave it in the radical form, which is the square root of 2/2, and the negative square root of 2/2, which is how you get those 0.707s. An arc T measures 7π/6 radians and terminates at a point on the unit circle as shown. Find sine t and cosine t. Construct a right triangle and label legs with sine 7π/6 and cosine 7π/6. So we'll take this point, we'll draw a line up to the x-axis, and then we have that radius there. The sine of 7π/6 is going to be this value here, and that's already right there, so I'm not going to write it again. And the adjacent side to the angle here is going to be cosine 7π/6. Then determine what the sine of 7π/6 and cosine of 7π/6 are using a calculator if necessary, and use these values to label the terminal point. The cosine of 7π/6 is negative square root of 3/2. And the sine of 7π/6 is negative 1/2. If you use a calculator, put these into decimal form, that gives you coordinates of negative 0.866, negative 0.5. The terminal point of angle theta on the unit circle is negative 0.6, 0.8. Determine the values of cosine theta, sine theta, and tan theta. If we paste in our unit circle, we know that this point here is at 1, 0, and this point here is at negative 1, 0. So negative 0.6 is going to be a little more than halfway to that point, and then 0.8 is going to be up here where the unit circle is. So we can draw this line there and this line there. Now this is going to be our cosine. We also draw that line. This is going to be our sine. On the next slide, we'll get into more of the details. All right, here's a nicer looking graph of our unit circle and our point. By definition, cosine theta is the x-coordinate and sine theta is the y-coordinate. So we have the point x, y is cosine theta, sine theta, which means that cosine theta is negative 0.6 and sine theta is 0.8. Tan theta is the ratio of sine to cosine, so sine over cosine. So here we have 0.8 over negative 0.6 gives us a tan value of negative 4/3. The terminal point of angle theta on the unit circle is at 15/17, 8/17. Determine the values of cosine theta, sine theta, and tan theta. Alright, so we can draw our point right here. 15 over 17 is almost 1. And remember, this point right here is at 1, 0. So this length, this cosine theta, is almost 1. And 8 over 17 is about half. So while this point is at 0, 1, this point's going to be a little less than halfway to 1. And that will be at 8 over 17. So we have our cosine and sine. We see that cosine theta equals 15 over 17, sine theta equals 8 over 17, and then divide those two values to get our tan theta, and that's 15 over 8. The standard arc T terminates in the second quadrant of a unit circle. The value of sine t is known, and the value of cosine t is unknown. Given that sine t equals 3 over 5, sketch a unit circle and label t, sine t, and cosine t. Use the Pythagorean identity to find cosine t and then find tan t. Alright, so on this slide, let's just figure out about where the point is. And on the next slide, we'll solve for cosine. Alright, so sine t equals 3 over 5. And we're dealing with the second quadrant here. So we know the point's going to be somewhere on this arc right here. 3 over 5 is a little bit more than half. 2.5 over 5 would be half. We know this point is at 0, 1. So this length here is 1. So the length here is going to be a little more than half. So we know it's going to be about there. So we go trace that over to the arc, and we see our point is going to be there. And then we can drop our lines down, and here we have our problem. On the next slide, we'll solve for cosine t and tan t. We can now use our Pythagorean identity to find cosine t, because here we have a circle. We know the length of this line here is 1. Since it's a unit circle, every radius that you can draw is 1, a length of 1. So we know that sine squared t, so this length squared plus this length squared is going to equal 1 squared, which is 1. So we can solve for cosine t, and we see that it's positive or negative 4 over 5. Now, in quadrant 2, cosine values are negative. So the answer is going to be the negative answer, negative 4 over 5. Then to find tangent t, you just take sine t and divide it by cosine t. So 3 over 5 divided by negative 4 over 5 gives us negative 3 over 4.